Alrighty. So now we're on 3.3, comparing linear and exponential growth, right? So 3.1 kind of defined what exponential growth and decay are. 3.2, we talked about changing the time period from maybe like 3 hours to 15 minutes and stuff like that. And then we saw how we could apply that to interest rates and compounding interest. So now, previously we saw the average rate of change of fx is, you guys remember AROC, our average rate of change. We know that that is defined as f of a minus f of b over a minus b. Okay. So 1 second, move something out of the way. Okay, good. This is my first time recording on my new laptop, so I need to make sure everything's okay. All right. So that's what we know so far. We already know how to find the average rate of change. So if A and B are 1 unit away from each other, so we can say that A is like X and B is like X plus 1. If we plug that into our average rate of change, we would have like f of x minus f of x plus 1 over x minus, oops, did I do this right? Yeah. X plus 1, which is going to equal f of x minus f of x plus 1 over, this is going to be x minus 1, so minus 1. So we can really just say f of x plus 1 minus f of x. So that would be our average rate of change in a function where a and b are 1 unit apart. All right. So the growth rate of f, so right, we're assuming, we're talking about exponential functions, we're assuming that f is exponential growth. So the growth rate, remember r, that's going to be f of x plus 1 minus f of x over f of x. If you hear rumbling, it's like that Friday after your second exam where there was huge storms and Duke's kind of freaking out. All right, so that's the definition of r that we were first given. And then from there, we can get like a minus 1 out. All right, so I kind of mentioned this before. The way I remember this is like new minus old over old. New being like the one right after, because x is in time period. So the new time period minus the old one divided by the old one. Okay. So the growth rate is going to be similar to what we call the percent rate of change. So remember, I've kind of said this before, we have lots of different rates of change. Average rate of change, percent rate of change. There's also an instant rate of change, things like that. So when you say rate of change, sometimes you need to be specific, especially when we're talking about percent rate of change. All right, so percent rate of change is going to be f of x plus 1 minus f of x over f of x. And this is percent rate of change for any function, okay? It just so happens that when we're talking about exponential functions and growth and decay models, that our percent rate of change also matches r. So we could say that our PROC equals r, the growth and decay rate, okay? So if it's a decay, growth or decay model, then this will happen. So we need to first meet this first criteria to have this second criteria met, okay? If it's a linear function, its percent rate of change isn't going to be the same every time, okay? Only if it's an exponential, which is growth or decay model. All right, so let's find the average rate of change and percent rate of change for the function f of x equals 10 times 3 to the x on intervals of length 1 starting at 0. So what we're going to do is we're going to make a beautiful chart. So we're going to have x, f of x, and then we're going to have our average rate of change and our percent rate of change. Okay, cool. So we're starting at 0. So 0, 1 on intervals of length 1. So then 2, 3, 4, and maybe we'll do all the way to 5. All right. So my function is 10, starts at 10 at 0, and then it triples every time. So then it's going to be 30, 90, 270. Okay. Now I need my calculator. Oh wait, no, I have it in front of me. And 81. And let's not do 5. That seems like plenty. Okay. So now I'm doing average rate of change. So for the first one we know we can't do, we're going to do the average rate of change of like that one and the one above it. So this is going to be 30 minus 10 over 1 minus 0. So it's going to be 20, and then it's going to be 90 minus 30. So 60, 270 minus 90. And I'm not dividing by anything here like we normally would, just because I'm going to divide by 1. So just saving a little space. 270 minus 90. It's going to be 180. And then 81. 810 is going to minus 270 is going to be 540. So definitely not a linear model, right? Our average rates of change are not consistent. Well, let's look at the percent rates of change. So we use average rate of change to identify linear functions. So let's see if I'm being presented a percent rate of change with a new type of function. I think we might be looking for something similar to the comparison between average rate of change and linear functions. So I want to do 30 minus 10 divided by 10. So that's 2. And that would be 200%. Okay. Percent rate of change. They're going to have percents. Just like we talked about R being described in percents as well, because it's a rate, like an interest rate. So then you can notice that each time I need to do f of x plus 1 minus f of x, it's just going to be this value. And then I'm going to divide it by that guy. So this is going to be 60 minus 30, which is 200%. And that 200% comes from me getting 2, and then it's a percent. So it's divided by, I need to make it a percent. So it's like 1 divided by 100. I would multiply it by 100, and that would give me my percentage. Okay, 180 over 90. Yep, that's 200%. And then 54 divided by 270. That's also going to be 200%. So, oh God, there's a big flash of lightning. Okay. So average rates of change are changing every time, but our percent rate of change is constant. Okay. So that's good to know. So what is the average rate of change? How does average rate of change for linear models? So it's kind of what I've already harped on already. So linear functions or linear models, kind of the same thing. Oh, there's a rumbly, sky boom. Linear functions have constant AROCs. Yeah, the table's like shaking. And then we just saw from this exponential function that that's going to have percent rates of change, so that we can kind of take it one step further and say that exponential functions have constant percent rates of change. And it really, since we talked about earlier, if it's an exponential decay or growth model, then the percent rate of change equals R. Well, R isn't changing depending on X at all. That's not changing each thing. It's always the same for the model. So it makes sense that it would have a constant percent rate of change since R isn't ever going to change. Similar to like linear functions are going to have constant average rates of change, because remember the average rate of change we saw was M. That's our slope. This M doesn't change unless it's a piecewise function, but like it's not changing at all. It's a set constant in that line. Okay, so now we're going to go through a few examples, and we're going to see which is linear, exponential, or neither. So that means we need to check all three. So, and we need to check all the way down too. So just because the first two look like they have a constant average rate of change, the third linear, the third one might not. So we need to make sure that all of them are the same, all right? So we're not going to do the first one. So we're going to do 4 minus 1 over 2. So that's going to be 3/2. 16 minus 4 over 2 is going to give me 6, and 64 minus 16 over 2 is going to be 64 minus 16, 54 minus 6, so 48 divided by 2, which is 24. And if you wanted to just put like an X on it, I'd be like, not that one, not, there's no constant average rate of change there. So if we go to percent rate of change, we're going to do 4 minus 1 over 1. So it's 3. Let me just check. Okay, yeah. So yes, okay. And then 16 minus 4 over 4 be 12 over 4, which is 3. And then 64 minus 16 over 4, which would be also supposed to be 3. Forty-eight divided by 4 is 12, though. Let me check on that for a second. Did I write this wrong? Oh, not divided by 4. I got carried away. Divided by 16. Duh. Okay, great. That's what I wanted. 3. So this model's right, this function, here we go. This function represents an exponential model. And then if you wanted to, you could say such that R equals 3, or percent rate of change equals 3. And that, as you can see, like every time I'm just multiplying this by 4. 1 times 4 is 4, 4 times 6, 4 times 4 is 16, 16 times 4 is 64. Remember, R is just 1 less than A, so it makes sense that R would be 3. Okay, and this, excuse me, should be 300. All right, so let's do the next one. give myself a little bit of room. Alrighty. So let's do it again. 2 minus 1 over 1. That would be 1. 3 minus 2 over 2 minus 1 is 1. So that's 1 again. Remember, like I said, we need to keep going. 9 minus 3 over 1 is going to be 6. And 27 minus 9 over 1 is going to be 18. 18. So for the first two, looked pretty good. But after the second two, it wasn't. And it needs to be constant all the way through, not just for a little bit. So that is not a linear function. So let's do our percent rate of change. 2 minus 1 over 1. So give me 100% or just 1. 3 minus 2 over 2. That's going to give me 1/2, which is the same as 50%. And then 9 minus 3 over 3 is going to give me 200%. And 27 minus 9 over 9 is going to give me also 200%. So again, these two match, these two match. So it looks like it's going from like a linear to an exponential, but we want to know if I can model the whole entire function using just one of those models, and I can't. So we would say this function is neither linear nor exponential. Okay. Now we have one with decimals, so it might be good to use your calculator for this one, okay? Remember, we always kind of want to show this whole chart. Okay, so we're going to do average rate of change, percent rate of change. There we go. All right, so 4.5. So each one of these x's is moving by 1. So everything's going to be but 1 on the denominator of our average rate of change. So 4.5 minus 2.8 is 1.7. And we'll do like 6.2 over 1 minus 4.5 over 1 is also 1.7. Looking good. 7.9 minus 6.2 over 1 is also 1.7. And 9.6 minus 7.9 over 1 is also 1.7. Perfect. So it does have constant average rate of change. But let's just check our percent rate of change just in case something else happens. So, and also just get some more practice. So 4.5 minus 2.8 divided by 2.8, that is going to be 1.7 over 2.8, which is 60%-ish. And then this would be like 1.7 over 6.2. Not 6.2, 4.5. Which is going to be like 38%. So we can already tell that that is not a constant percent rate of change. And then we can keep going if we wanted to practice, right? So dot, dot, dot. And then since our average rate of change was constant, we would say this for the function has a constant average rate of change, and thus is linear or represents a linear model. All right, beautiful. Okay, so let's go through this really fun example. So city officials in Newburgh, population 10,000, wish to make a long range plans to maintain and expand infrastructure. Great job. Sorry. And services of their city. They hired 2 city planners to construct models for Newburgh's growth over the next 5 years. Okay, so planner A estimates the city's population increases by 500 people each year. So far we only know 2 types of models, linear and exponential. So planner B estimates the city's population increasing by 5% per year. And then we're asked to find a function that models planner A's idea and planner B's idea. So since we only know linear models and exponential, and I'm given 2 planners, those are going to be my only models I can choose from. So I have an initial condition of 10,000 for each one of them, which is great. So this planner A estimates the city's population increases by 500 people each year. So is it going to be a linear model or exponential? I think it's going to be a linear model because by 500 people each year. And this one gives me 5%. I see a percent, immediately that's R, right? That gives me a rate in a percentage form. And I've only ever seen that in exponential models. So we're doing linear. So we have y equals mx plus b. Remember, b is our initial value. So b is going to be 10,000, but what's m? Well, planner A thinks I'm going to have 500 increase by 500 people each year. So every year I'm going to add 500. If you go back and look at our first few sections talking about linear models, that's the definition for that. I think it was called like big A in front of X. It was the change in our output by moving X 1 over. So in 1 year, so each year. So that tells me that M is going to be 500. You could have also drawn, we would call this like A of X if we wanted to. 0 and 10,000. 1 is going to be like 10,500. 2 is going to be like 1,100 and so on. You could have found the slope between either of those things and you would have gotten 500 as well. That's a more literal approach. Okay. So instead of using Y, let's use A of X. So A of X is going to equal mx plus b. So A of X is going to be 500 X plus 10,000. Okay, that's kind of in the way. And we can go and check ourselves by looking at that chart that we made over here, which is again kind of like checking yourself against yourself, which is a little bit harder, but if I'm increasing 500 a year, I'd go 10,000, 10,000 plus 500, and then plus another 500, plus another 500, bum, bum, bum. Okay. So that's planner A's idea. That's his model. Planner B estimates the city's population increases by 5% per year. So this one, if we're choosing between linear and exponential, it's going to be exponential because I see that percent there, and that immediately tells me if it's 5% per year, that's telling me it has a constant percent rate of change. Just like 500 was telling me that there is a constant average rate of change. So that 5%, that's what R is going to be. It's 5%, or we can write it in our decimal, 0.05. Okay. So let's call this one B of X. Our linear, our exponential models look like C times A to the X, right? So C here is going to be our initial condition again, 10,000. Okay, but what's A? Well, remember that A is just one more than R. So it's going to be 1 plus 0.05, which is 1.05. So we can put that all together and I'll get that B of X is 10,000, 1.05 X. And this, a good way to remember that A, like it's going to grow. So we know that A needs to be greater than 1 because we're told the population increases. And we know from 3.1 that if A is less than 1, then it's going to decay, meaning R is negative. And if R is greater than 0, it means A is going to be greater than 1. It's going to grow. And increase, grow are synonymous. Okay. So that's why I know it's going to be 1.05. Great. So now graph the two for the next 25 years. How do they differ? So I don't know about you guys, but my artistic skills are atrocious. So I'm going to pop over to Desmos. There's Winston. And that was one more problem. So we're going to look at 500. Oops. Let's do y equals 500x plus 10,000. And we want to do it over the first 25 years. So on Desmos, you can like move this over a little. There we go. If I hold onto the axes and pinch, I can also bring this bad boy down. So there we go. Looks a lot more reasonable. So then y is going to equal 10,000 times 1.05 to the x. Great. Beautiful. I think that looks great. So I like to click on them. Where do they intersect? Those 2 points. That makes sense that their initial condition would also be the same. Okay. So that's them over the first 25 years. And I'm actually going to leave that sidebar in just so we can remember who is who. Paper. Oh, no, I want to add a picture for the library. There we go. Okay. We'll put that right there. Can you guys see that? Beautiful, lovely. What was I looking at? There we go. So how do they differ? So we can say like in the beginning, the models were similar, but B of X, you can say grew much quicker than A of X. Basically, just kind of describe what the graphs are doing compared to each other. I would like, they look about the same for the first maybe like 4 or 5 years. The models were similar. Say like first 5 years. That's like an approx thing. But eventually B gets really, really big. And that's like when we say like exponentially fast, it means like really fast. Okay. So exponential models are great, but we can see that this keeps going on and on and on forever and ever and ever. I don't know if a city could hold so many people eventually, right? So that leads us to our next type of problem. So a cell phone company has sold 3 million phones this month. Wild. But the company president would like for his sales force, excuse me, to double their efforts and double sales every month. Ugh. This means that sales would grow exponentially, right? It's doubling for each specific time period. So doubles per month. If this were to happen, they would sell nearly 12 billion phones in the 12th month, and they need to double it the next month. That's more phones than people on Earth. And I don't know about you guys, but I literally just have one phone. I've had the same phone for like 4 years. So an exponential function isn't enough. It's growing exponentially, but I need to cap it off at some point. All right. So I don't know why I left that blank there. So we have a similar exponential model now. And this one is called oh God, sorry. Someone sneezed. Logistic growth model. So logistic growth model is of the form. So I'm gonna call it f of x because it's a function. We have C. I don't like calling it C because it's not our initial condition. Over 1 plus B a to the negative x, where a is greater than 1 and b is greater than 0, right? So and it models growth under limited resources. So I think we talked about a problem with like chinchillas or bunnies, and we were like, the bunnies can have unlimited food. There's no predators, so there's no cap on the resources, and no bunnies were going away. They lived forever. It's like the farm that your parents tell you where your pets go. So X here is still going to be the number of time periods, right? Like per month for that problem that we just saw before, maybe like years or several years, decades, whatever. All right. C is now carrying capacity, right? You can't really change the letter because like the thing is called carrying capacity. Those things both start with C. All right. So carrying capacity is the maximum amount of populations the research can support. It's the maximum, it's the at capacity that the resources can carry, right? My carrying capacity is like 2 grocery bags. Okay. But if I go work out, my carrying capacity can be more, but right now it's 2. So carrying capacity, I can't go over that. Resources won't happen. Then people start starving or bunnies start whatever. You get the idea. Okay. I don't want to talk about bunnies being like that. Sad. Okay. So now, oh God, why that scared me so much. So the graph is still going to kind of look exponential, but that carrying capacity is really important. So let's call this it's going to be C, my carrying capacity. And my function is going to be kind of down here, and it's going to grow exponentially. And then it's going to flatten off. It's never really going to hit that carrying capacity. It's going to get really, really close. Obviously, in real world things when we can only have whole numbers, I can't have half of a bunny. It can hit that, but this graph isn't going to. Call that f of x. So C, y equals C, that line, remember horizontal lines are y equals, is what we would call, okay, it's an asymptote, right? Functions that have asymptotes like this one are what we call asymptotic. It's one of my favorite words. It's so fun to say, asymptotic. Okay, so C is no longer our initial condition here. To find our initial condition, we just have to plug in x equals 0. So it'd probably be like C over 1 plus B. That would be our initial condition. C now equals our carrying capacity. I can never go over that value. That's the biggest value that f of x can be. So if you get a number bigger than their carrying capacity, you know to check your work. All right, so then, and fish. A biologist models the number of fish in a small pond by the logistic growth function. F of x equals 100 divided by 1 plus 9 times 1.5 to the negative x. Okay. So where x is the number of years since the pond was first observed. So what is the initial number of fish in the pond? In So in our logistic growth model, C is no longer our initial condition, our initial value. Our initial is going to be whenever x equals 0. So when at 0, which is going to be 100 over 1 plus 9 times 1.5 to the 0. Anything raised to the 0 power is just 1. So this is going to be like 100 divided by 10, which we know is 10. So what's the initial number of fish? We would say 10 fish. Fish is like the plural of its own, like moose. 1 moose, 2 moose. So what's the carrying capacity of the pond? What's the maximum number of fish that I can have in the pond? It's going to be that C. So our carrying capacity equals C, which is 100. So 100 fish. We started off with 10, and the pond is so big enough that it can only produce so many algae and so much space for 100 fish to live comfortably. All right. So now we're going to make a table and we're going to graph our function, right? So you do this with your calculator, but if you were, you get approximately these numbers. I've rounded a little bit. It'd be like 10, then 14. I'm just plugging into our calculator. I've already done this, so you don't have to like just sit and watch me plug in numbers to a calculator. 36, 46, 86, 98, and 100, right? So that would mean that our graph would kind of look like boop, this guy. So we would start at 10. Here's 100, and it took 20 years to get to its carrying capacity. So we'll put like 20 down here. And we're just gonna go boop, boop. Like that. Let me draw. Pretty nice, pretty nice. All right, and that's what our graph kind of looks like. I'm not expecting artistic level work here. Okay, so that's how we can use exponential models to model something that then kind of has a limit. So that's why we've introduced logistic growth models. I don't really think that you guys are going to be able to come up with a logistic growth model on your own, unless it was like fill in the blank and it tells you the carrying capacity is something, you just fill in for C like that. Okay. So that's it for this one. I will see you guys for 3.4, which is your second lecture of the day. Okay, bye.